Alright, so today I'm going to be explaining another important article with the title Spectral Clustering with Graph Neural Networks for Graph Pooling. So this paper in ICML 2020 by Bianchi. Spectral clustering is a popular clustering technique to find strongly connected communities on a graph. And it can be used in graph neural network to implement pooling operations that aggregate nodes belonging to the same cluster. However, the eigendecomposition of Laplacian is expensive, and since clustering results are graph-specific, pooling methods based on spectral clustering must perform a new optimization for each new sample. In this paper, we propose a graph clustering approach that addresses these limitations of spectral clustering. We formulate a continuous relaxation of the normalized mean-cut problem and train a GNN to compute cluster assignment that minimize this objective. Our GNN-based implementation is differentiable, does not require to compute the spectral decomposition, and learns a clustering function that can be quickly evaluated on out-of-sample graphs. From the proposed clustering method, we design a graph pooling operator that overcomes some important limitations of state-of-the-art graph pooling techniques and achieve the best performance in several supervised and unsupervised tasks. So you see a deep GNN architecture where message passing is followed by min-cut pool layer. Then again message passing, then again min-cut pool layer, then again message passing. So we do it hierarchically. So we propose a graph clustering approach that addresses the limitations that hinder applicability of this spectral clustering in GNNs. And so the output of MP, message passing, is X bar. But the KV normalized mean-cut problem is the task of partitioning the in K disjoint subsets by removing the minimum volume of edges. So we just need to maximize this objective. And you see the numerator counts the edges, the edge volume within each cluster, and the denominator counts the edges between the nodes. So if C is a cluster assignment matrix, when it is 1, it means that node I belongs to cluster J and 0 otherwise. So the mean-cut problem can be written like maximization of this one. So each node belongs to one of these K clusters. So you know that this problem 3 is NP hard. It's NP hard, and but in a continuous relaxation, it can be solved in polynomial time. This is the good news. So it guarantees the near optimal solution using this relaxation. So now we have polynomial time solution. So while problem 4 is still non-convex, there exists an optimal solution. So we know this is the optimal solution, and U are the eigenvectors of A. That corresponds to the K largest eigenvalues. And O is an orthogonal transformation. Spectral clustering obtains the cluster assignment by applying k-means to the rows of Q star, which are node embedding in the Laplacian eigenspace. One of the main limitations of spectral clustering lies in the computation of spectrum to obtain Q star, which has a memory complexity of order of n squared and computational complexity of O(n) cubic. So this prevents its applicability to large data sets. So now you understand that spectral clustering uses k-means to the rows of Q star. But spectral clustering, first you should calculate the spectrum to obtain Q star. But this calculation of the eigenvectors, it has a square order of n squared, memory complexity, and a computational complexity of O(n) cubic. So that's why many people cannot use this in some big graphs, some practical applications. So to deal with the scalability issues, the constraint optimization for this one can be solved by gradient descent algorithm. So we have converted the problem to an optimization problem. Because if you do that, then you can immediately solve it using gradient descent. So that is the motivation. So can be solved by gradient descent algorithm that refine the solution by iterating operation whose individual complexity is order of n squared. So these algorithms search solution on the manifold induced by orthogonality constraint on the columns of Q by performing gradient updates along the geodesics. Alternative approaches rely on QR factorization to constrain the space of feasible solutions of the factorization by ensuring that orthogonality holds only on one mini-batch at a time. And so some discuss the equivalence between graph clustering and kernel k-means. And their Grackless algorithm is a popular model fee for hierarchical pooling. So to learn a model that finds an approximate spectral clustering solution also for out-of-sample graphs, several works propose to use neural networks. For example, this one, an autoencoder, is trained to map ith row of Laplacian to the ith component of the first k eigenvectors. And he define an orthogonality constraint to learn spectral embedding as a volumetric reparametrization of a pre-computed Laplacian eigenbasis. And in 2018, it proposes a loss function to cluster generic data and process out-of-sample data at inference. While these approaches learn to embed data in the Laplacian eigenspace, they rely on a non-differentiable operation to compute the cluster assignment and therefore are not suitable to perform pooling in a GNN trained end-to-end. So X bar is the matrix of node representation yielded by one or more message passing layers. And we compute a cluster assignment of node using multi-layer perceptron. Now, instead of GNN that they use in diffpool, they are using multi-layer perceptron to reduce the computational complexity. So this is good. And then they have this loss because LU composed of two terms which approximates the relaxed formulation of mean cut. So the cut loss, the first term is called cut loss that we have discussed, evaluates the mean cut given by the soft cluster assignment and is bounded by -1 and 0. So minimizing this cut loss encourages strongly connected nodes to be clustered together, since the inner product increases when A tilde is large. And L sub C has a single maximum, reached when the numerator is 0. And this occurs if for each pair of connected nodes, A tilde, for example, is greater than 0, the cluster assignment are orthogonal, and the cut loss reaches minimum -1 when the trace of S transpose A tilde is equal. So when the numerator and denominator is equal, so that is the minimum of this. However, L sub C is non-convex, and its minimization can lead to local minima or degenerate solutions. For example, so this is the schema of mean cut. As I said, they used MLP instead of another GNN to get S, the cluster assignment. So it's an improvement to diff pool. Also, it uses mean cut objective, which is theoretically very rich in computer science. And then the Coarsen adjacency matrix and pooled vertex features are computed as follows. So the rest of that is obvious. So it is important to note that since mean cut pool computes the cluster assignment component, cluster assignments from node features that become similar to the message passing operations, clusters are likely to contain nodes that are both strongly connected and with similar features, reducing the risk of finding a degenerate solution. So the space complexity of mean cut pool layer is just order of nk. K is your number of clusters. And n, is the number of nodes always. So it's pretty good. That is good. But diff pool, is a pooling method that uses message passing to compute clustering. And it was one of the first attempts to learn it that I explained in the previous video. The approach dubbed by top K pooling learns the projection vectors. So we conduct an in-depth comparative analysis of mean cut pool, diff pool, top K. So this is important. For example, SAG pool, I've explained it in a different video. Diff pool was last video, top K another video. And mean cut pool, this is this video, this paper. It is an improvement to, for example, for let's say protein, from 72, you have 4% improve. For protein. What about DD? It's just 1%. Yeah. And what about collab? It's just 2% improvement. What about Reddit? Oh, it should be higher. So nice. So this is the architecture schemata. Figure 8 depicts the GNN architecture used in clustering segmentation tasks. You can use it for graph regression, and this is the architecture for the autoencoder. They also discussed this one.